All right, students. So what we will do today is discuss this problem on the topic of transformers. And this is a very important topic for your board examination. So I will not restrict myself to the only to this topic, but I will go beyond this and make you understand the concepts of transformer. It is very important topic, and the idea is to not only restrict ourselves to the discussion of transformer, which is given in this case study, but really understand the transformer so that you develop conceptual understanding, which helps you score very well in your examination. And the way you have to look at case studies is, you should have conceptual clarity, which is what is the aim of this video. To put in your mind, what is a transformer? How does it work? So without wasting any further time, just one request, please don't forget to subscribe to this channel, because this is the only channel in the country which is giving you content which is real with explanation. Okay. Now let's read through this case study. So I have to read this on the projector. You can read this on the screen itself, right? Now, for many purposes, it is necessary to change the or transform an alternating voltage from one to another of greater or smaller value. This is done with a device called as transformer using the principle of mutual induction. Very important paragraph. Okay. Why is it? It says for many purposes, it is necessary to change an alternating voltage from greater or smaller value, right? You know, transformer steps down the voltage and steps up the voltage. But why does it do that? Let me give you an example. In a country like India, a lot of power which is generated in the power station gets wasted before it reaches your house. Okay. In order to distribute the power for which you pay the bill from the power station to your house, what we do is we increase the voltage of the power. Okay, so power is V into I. I increase the voltage of the power. That means I'm reducing the current. The reason is I want to reduce the I square R losses. So one of the important purposes of increasing the voltage is being able to transmit the power economically. So what you do is you generate your power at a certain voltage. Okay, this is the voltage with which you generated, and this is your generation plant. Okay, what you do is before it hits your house. Okay, this is your house. Before it hits your house, we increase the value of this voltage by using a transformer. This is a transformer. This increases the value of the voltage to say 330 kilovolt. It's a hypothetical number. But this voltage, which was generated by the power plant, is very low. You have to increase the voltage by using a transformer. Now the current is low, and therefore the I square R losses in the transmission wires are very low, right? Otherwise, what will happen? You will generate X amount of power and only X by 2 will reach your house because I will be very high. How do you reduce I? What you do is you are saying power is V by I, which is generated by the station. You increase this, okay? You increase this to a very large value, and therefore you decrease this. Okay? This goes down drastically. When this goes down drastically, what happens? The I goes down, so I square R loss in the transmission wire goes down. So it is necessary for us to increase voltage like we did here to distribute the power in an economical manner. It is very cheap. Otherwise, 50% of the power will get wasted if there is no transformer. The transformer increases the voltage to reduce the current. Current goes down, I square R losses go down. Very important. A numerical is given in NCERT about this, the power distribution to houses. Please do that. It is solved in my playlist also. So now you understand that what is the purpose of transforming voltage. And there are cases where voltage has to be brought down. Okay. So I'm not going to get into detail of when it goes down. An example of power distribution. And then in the same breath, we can say finally at your home, the voltage has to be brought down. So near your home also, there will be a transformer to reduce the voltage. That is also very important because your devices work on low voltage. Now we understand the purpose for which the transformer increases the voltage or decreases the voltage, right? That is one. So we have understood the para one. I'm not strictly going as for the case study like 1, 2, 3, 4. I'm also explaining you what is written so that your conceptual understanding of the transformer increases, which will help you solve the case study very easily. Let's go to the para 2. A transformer consists of two sets of coils insulated from each other. Now this is very important. There are two coils. I hope you know that, right? So generally, the transformer is shown like this, right? You might have seen the way a transformer is shown, right? So you have a primary, right? And then you have a second, okay? This could be what? 100:1, which is your turns ratio, NP and NS. We will discuss what is the meaning of this. But there are two coils, primary. So on the primary side, you have primary current, and on the secondary side, you have I secondary, right? And this is where your actual load is there, right? Which wants the voltage up or down. In this case, since the primary is higher and secondary is low, it's a step down, right? We'll discuss that. Don't worry. So now, this is the way a transformer looks like. And generally what happens is, you also have a situation where So you also have a situation where, so these two, okay, primary and secondary, why are they there, right? Let's go through the third paragraph. Okay, and they're insulated. The number of turns is given, they're insulated so that there is no short circuit. Very important. And there is spacing also. Okay, spacing. Okay, so every coil is spaced from each other. Now let's go to the third paragraph. There was not, okay, it says it is wound on a soft iron core. Soft iron core, why? Because the iron core which you have, which is this, okay? The iron core which you use, where you wind this up, okay? Right, this is the way you would see. So this is a core. Why do you have soft iron core? So that the flux which is generated by the primary, because of the current in the primary, this flux travels very easily to the secondary circuit. There are two circuits here. When we say there are two coils, we are saying there are two magnetic circuits, circuit number 1 and circuit number 2. The circuit number 2 is the secondary coil. The circuit number 1 is the primary circuit. Electric circuit? No. Magnetic circuit. Because what we are talking about is the flux which is traveling from one circuit to another. And for traveling of the flux, we use the soft iron so that there is no leakage. If there is no soft iron, the flux which starts from here may not be fully able to reach the secondary coil. Okay, it may not be able to reach this. A lot of flux may get lost and may go here and there, right? So it may go here and there. But if you have iron, which has very high permeability, which is allowing the flux to easily go through the core and reach here. So I hope you understand that the use of soft iron is to have high permeability medium between the two circuits which are linked to each other through the same flux. The flux is same. The rate of change of flux is also same. And this magnetic linking is called as mutual induction. See the first paragraph, last word. Mutual induction is what you will see. Right? This is mutual induction. So one is sending flux to another and inducing a back EMF in the secondary also, right? So, okay, let's go to the next paragraph. I hope you're understanding the each paragraph and the importance of the words. We will come to the questions, but let's increase our conceptual understanding. Let's go to the next one. Often, the primary coil is the input coil. I told you, right? So, here, this is the input. So, generator which produces voltage is an input to the transformer. So it is giving some voltage to the transformer and transformer is increasing it. So you need an input source which is alternating. Remember, if you connect a DC here, nothing will happen. Okay, so we are talking about transformer used with alternating current. You don't have transformers for DC. In our course, not there can be any such mechanism. So there may be mechanisms in other branches of physics, but we are talking about alternating current here. We're studying the normal transformer we see in our daily life, and therefore we are dealing with alternating current as the input. So this is V primary. Now the V primary produces I primary, and since it is alternating, it generates a flux here, which is also changing because you have L di by dt, and therefore you also have N d phi by dt. If you have N d phi by dt here, and the same rate of flux is connected to this, you also have N d phi by dt on the other side. So both the sides have their N primary d phi by dt, N secondary d phi by dt, and are magnetically coupled, the two circuits, by the process of mutual induction. I hope this is making sense in your brain. All right. So when an alternating voltage is applied to the primary, the resulting current. So when you're applying current here, right? So this current is producing a flux here. Okay, so flux is getting generated. You can use a right-hand rule and find out the direction of the flux up or down. Okay, which links the secondary. Okay, which links to the secondary through the soft iron. It's not mentioned soft iron, but that's a mechanism. It links and induces EMF in it. So you have an EMF which gets generated in secondary. Okay, because the moment it starts getting a d phi by dt, it starts getting a d phi by dt from the primary. It also induces a back EMF, right? All right, we've understood that finally the magnetic coupling, the d phi by dt coming from the primary will get passed on to the secondary. The d phi by dt of primary will get passed on to the d phi by dt of the secondary. We have understood that, right? And now what happens is it produces a back EMF in the secondary. Let's go to the last paragraph. Okay. Now it says the value of this EMF, the EMF which is generated in ES, depends on the number of turns in the secondary. Of course, if you want to write the EMF value, in the secondary, you will write it as minus N secondary d phi by dt, right? Or minus ns, the area will go out. Phi is equal to b into a dv by dt. So it's a time varying flux because you have alternating current, you have a sinusoidal situation of voltage. Voltage is equal to V max sine omega t. So and it produces an alternating current and therefore an alternating flux, and therefore the back EMF which is produced is Na dV by dt, where V is the time varying magnetic field coming from the time varying signals. Okay, you can leave it here if you understand this. So the back EMF which is generated in secondary is proportional to the secondary turns. I hope this is clear. Now it says we consider an ideal transformer in which the primary has negligible resistance. Oh, okay. Now let's focus on this statement. So primary has negligible resistance. I would go to the extent of saying that even the secondary has negligible resistance, because we're talking about ideal. Why? Because we want to avoid the copper loss. We don't want I square R losses happening here. So we don't want I square R losses in this wire because it has a resistance also, remember. And similarly, we don't want I square losses here also. Remember, even this has a resistance. We don't want this. Why? Because the efficiency of the transformer will go down. If I am producing 100 kilowatt of power and the power is moving from this place to this place and we're only getting 50, right? Some amount of power is getting lost here in the wire, but some amount of power is also getting lost in the transformer. Even here where you have a step down transformer, step down near your house, right? You will have power. So there happens a power loss inside the transformer. So transformer itself is consuming the power which is it was supposed to pass on to the consumer for the actual benefit. And here also the transformer, which is a step up transformer, is consuming the power. You have reduced the current, but still you still have I square R because R is very high. So ideally you would like your transformer coils, both primary and secondary, to have very minimal resistance. Okay, let's talk about another situation. All right, now it says, and all the flux in the core links both primary and secondary winding. Now, another loss that happens in the transformer is the non-load loss, which is not I square R, but magnetic leakage. Okay. Now, that loss being referred to, actually, let me just redefine it. When you magnetize this particular, so there is a d phi by dt here, and there is a d phi by dt. Both are identical d phi by dt's because the phi is linked. The continuous magnetization and demagnetization of the core, okay, the continuous magnetization and the continuous demagnetization alternatingly results in a loss which is in the core itself, right? This is kind of magnetic loss which is happening, right? And this loss also has to be accounted for. It reduces the efficiency or working of a transformer, okay? And the third one is the flux loss. So there are three losses. One, the load loss, which is your I square R. Second, you have non-load loss because of the continuous magnetization and demagnetization of the core. You should know about it briefly. Third is a flux, which is again very simple. The point is the flux which starts from the primary does not reach secondary. The flux which starts from primary does not reach secondary. Such a difference in the primary flux and the secondary flux results in loss of flux. Why it happens? These may be very far away from each other. So the two coils, this coil is here, right? So this coil is so far that the flux is not able. But you do have a mechanism of soft iron to take care of this. But somehow you still have magnetic leakage, which is happening in the transformer. That also transforms into inefficiency, right? It also results. So all the losses, the load loss, the non-load loss, and the magnetic flux leakage loss are the type of losses. So I think the word for non-load loss is the core loss. It's a core loss. We will talk about it. So I hope I'm giving you good explanation. You are able to understand how the transformer works. You are essentially sending power from one side to another side with the help of flux linkage. Electrical, magnetic, back to electrical. So left side is electricity. The middle part, which is the core, which is this, you know, sometimes shown like this, okay, is the magnetic part, which is where all the flux is there. So the whole current gets converted into flux, reaches the other side. That flux then generates electricity of higher voltage or a lower voltage, depending on your ratio. Whenever you have a situation that the primary turn is greater than Ns, it's a step down, which means on the secondary side, less amount of voltage will be generated. And if you have the secondary, which is greater than Np, you have a step up transformer. You should know that the power which is generally transferred, okay, is not 100%. So we will have inefficiency, and therefore you may get questions on calculating the efficiency of a transformer. What you need to do is you have to calculate the power here and the power here and see if there are any losses given, right? Because inefficiency means the power you had sent across to the magnetic circuit got lost in the form of those iron losses, core losses, and the magnetic leakage. And therefore, the other side received less power. So you can have questions of step up, step down, depending on the turn ratio. And also you can have questions on power loss. Okay? Do these questions. In my playlist of transformer, you will see these questions being solved and clearly explained. Now let's come to the next part of it, which is the questions, okay, which may come in your examination. I hope you can read this. Very difficult for me to read, but let me try. So if the primary coil of the transformer has 100 turns and the secondary has 200 turns, then Ns by Np is equal to 2. Thus, a 220 volt input 10A will. Okay, so the question says that the primary has 100 turns, right? So we are saying the primary has 100 turns. So you have 100 turns here, and then it says that the secondary has 200 turns, right? So the turn ratio is 2:1. Okay, it is 2:1. So Ns by Np is given to be 200 divided by 100 is equal to 2. And the input current, which is available to you from the primary side, is 10 amperes. Okay, so I primary is equal to 10 amperes. And the voltage on the primary side is 220 volts. The question is, what type of, okay, so the first choice, it's a step up transformer, output at 5 amperes. It's a step up to 660. It's a step down. So first of all, let's decide whether it's step up or step down. The turns on the other side have gone up, and therefore it's a step up transformer. For the same magnetic change, I mean d by dt, d phi by dt, d phi by dt is same on both the sides. The n is different. On left hand side, the n is np d phi by dt. On the right hand side, the e is equal to n secondary d phi by dt. If the d phi by dt is same, but the number of turns has gone up in the secondary, then E secondary is doubled, right? So I will say that on the secondary side, I am going to get 440. It's definitely a step up transformer. It's not a step down. So the choice number C and D are outrightly wrong. Now it says it's a step up at 5 amperes. So anyway, I think A should be the answer. And also remember that the power has to remain the same. Okay, so on the left hand side, what you have transferred is 10 amperes. 10 amperes. Okay, so 10 amperes. multiply by 220 is equal to 440 into I secondary, right? So this will become 2 and I secondary will become 5 amperes. Obviously, when you have increased the voltage by double to keep the power same, power can't be changed, right? You're throwing some power from the primary side to secondary side. Power doesn't change. The only thing may happen is some loss, which is not there in the question. So you have increased the voltage part of the power. The current has to be accordingly adjusted. You double the voltage, the current becomes half. Let's go to the second part. For an ideal transformer, okay, for an ideal transformer, ES by EP is equal to NS by NP is valid when the primary resistance and current are small. I think the resistance is small is fine, but primary current is small makes no sense. Why do you need a small current here? For what? Basically, he's trying to say that uh, the the current is small, right? You can have any current on the primary side. Resistance should be small to keep the losses of the transformer low. Yes, but you can have any current, right? You can't decide on what current will you give to the transformer. It depends on the power, right? Generally, you give for very so different transformers may be able to use different current. So there is no mandate that you must have uh, a small current always. I don't think so that you need a small current. I mean, if the indication is that small current will result in I square R to be low because I is very small, probably, but that is not the main reason. You may still have higher currents being used in certain situations. So, what you can control is resistance. I would say keep the resistance low, but current is outside my purview because it is decided by who uses the transformer. Okay, let's talk about the second one. The same flux links both the primary and secondary. I think we discussed as very little flux escapes from the core. Yes, this is an assumption, right? That the same, okay, he's talking about an ideal transformer. Yes, in an ideal transformer, there is actually no loss, leakage. Let's talk about the third. The secondary current is small. Again, see, secondary current is not in our control. Is not in our control. It depends purely on what type of transformer we are talking about. In the previous question we did, we never said 10 amperes. Here was a small current, right? So I disagree with this statement that the secondary current has. I will say that the resistance of the coil, the secondary coil, should be low to control overall I square R. But does it mean that I will reduce I for it? No. It depends. I is purely function of V into I, right? It is the I square R. R is in my control. I can change the wire of the secondary to control the copper loss. So my answer to this question is the choice number B, which looks to be more logical, that the flux leakage in the case of an ideal world is zero. But in an ideal world, current will be small. I don't think so. In an ideal world, both the resistances will be small. So my answer is B. Don't go by all the above. If he had said the secondary coil has small resistance, the primary coil has small resistance, I would have gone with it. But he has said current should be low, so I disagree with that. My answer to this is B. Do not go with D. Okay, let's go to the next part. If the secondary coil has less turns, then now the reverse. Okay, the secondary coil has less turns, so it's a step down automatically. We will have a step up, step down, neither step up nor step down. Both. How is it possible, right? How can you have a situation whether there is no step up or step down? Then it's not a transformer, right? Then you're passing on the power at the same voltage. If the windings have same amount of turns, you have 220 and you're passing 220. You're not increasing it, not decreasing it. Useless transformer. And it says both step up transfer and absolutely wrong, right? If you have, how can a transformer for a fixed turn ratio where secondary is less than primary, we have stepped down and step up at the same time. The step up is outrightly wrong. It has to be stepped down because I told you the EMF generated is N d phi by dt. The d phi by dt is common. The number of turns in secondary is lower than the number of turns in primary. So it's a step down transform. Okay. Let's go to the further questions. All right. I think we have already discussed this. So the last one, it says in the actual transformer, real life, inefficient, doesn't give you 100% efficiency. There is a loss. The small energy losses occur due to flux leakage. Yes, we discussed that. Resistance of the winding, we discussed that. The RS and RP have to be very small. Eddy current, I told you about the non-load loss, right? The continuous magnetization and demagnetization. But there is also a concept of eddy current also, which I'm sure you understand when a whole metallic piece is subjected to a changing flux, circular type of very small eddy currents come up, and therefore you need to laminate the transformer, right? Lamination of transformer is also very important way to overcome this loss, right? So that you can have pieces and you don't have place for eddy current to flow. Go and watch my playlist and understand eddy currents. I think we had forgotten about eddy currents, but this question brings back to the topic that apart from that magnetizing and demagnetizing of the core, you also have eddy currents losses. So my answer to this question is D. Yes, you have all the losses out there which exist in the transformer. I hope you enjoyed this case study. You could understand transformer is an economical way to send power from one place to another. There is a question in NCERT, which is a big question at the end, which talks about sending the power from the generation plant to your home with the use of two transformers. The wire length is given. Do that question, very important. I hope you have enjoyed this question thoroughly. Please also attempt reasoning and assertion questions on transformer. I will keep on bringing these case studies and reasoning and assertion questions, at regular frequency now, so that your confidence level to get a conceptual clarity as well as be able to do well in your board examination and score very high goes up. Okay. So the key is go into detail, go through my playlist, listen to my videos, and keep the book, in front of you. You will see that complete syllabus has been covered through my videos, and I have gone in detail and given actual explanation as to how to solve the questions, how to handle the conceptual questions, theory, numerical, reasoning assertion, case studies for multiple examinations. So I hope you enjoyed this video. Please don't forget to subscribe to this video. If you have someone in your family preparing for exams and physics is a problem, please do help them out by spreading this channel, and that will be highly appreciated. So thank you very much and look forward to meet you in the second case study. Thanks a lot.